classes we talk about the characteristic method for Cauchy linear, and before that we also talk about the characteristic method for a linear advection equation, or you can say advection equation, or you can say transport equation. Now we will take a quick look on this method because a lot of students were confused how we are doing so. So I would like to ask Camilo and Rebecca, you guys were present in the last class. So did you go through the notes and did you read the book? So it would be much easier if I revise it again. Camilo, Rebecca, did you revise the notes or anything if you have any doubts?
Yeah, I checked the notes yesterday, I think, and everything is clear, I think.
Okay. So we are just going to take a quick look and going to explain you, and it would be much easier for you now. So just see what was happening. What we took a Cauchy linear partial differential equation. So if you remember, we took this partial differential equation a x y z del z over del x. That is basically I call it p. That is a notation. B x y z del z over del y is equals to c x y z. So here you can see that the derivative of the dependent variable is of order 1. However, the order of z is non-linear. So you can see that the derivative of the dependent variable is of order 1, but its coefficients are function of dependent and independent variable, and also these are non-linear in z. These are non-linear in z. It might be of order n. So because of that, it is a Cauchy linear partial differential equation. And then we talk about the characteristic method. We talk about the geometry, how to solve this partial differential equation, and what will be the geometry, and in what case we are going to get a unique solution, in what case we are going to get a multi-value solution. So we saw that if I usually call it Z, but in American continent it is Z, but in European continent it is Z. So don't. So this z, that is your dependent variable depending on x comma y. So the solution of this Cauchy linear PDE will be z is depending on x comma y. So we know that this will, if this represents a point in 3D plane, so the locus of a point which depends on two unknown, which depends on two variable, is a surface. So this is going to be a surface in 3D plane. Now we can also write it z as a function of x comma y minus single z, that is say some function f that is equals to z. So we know that a gradient of any function represents normal to that surface. The gradient of any function f represents normal to that surface, that hypersurface what you are taking. So since this is a surface, so what will be the gradient? Gradient of f, that is del f over del x, that is nothing but del z over del x. Del f over del y, that is nothing but del z over del y. Del f over del z, that is nothing but minus 1. So this say I also denote it by p, and this is q. So this p comma q comma minus 1 is going to be normal to this surface, is going to normal to this surface. Now we know that if this is normal to the solution surface, if it is not, it is also known as integral solution surface. So if this is normal to the solution surface, then we can write this equation first as a comma b comma c dot product with, this is a vector field, that is depending on x, y, z. Dot product with the vector field p, q minus 1. Always keep in your mind that is p is del z over del s, q is del z over del y, or if u is dependent variable, then it can also be written as. So the derivative of the dependent variable with respect to x, I have given this notation p, and the derivative of the dependent variable with respect to y, I have given the notation q. So the dot product of this normal with this vector is going to be 0. It means if this is normal, then it is going to lie in the tangent field. So it is going to lie in the tangent field, because if the dot product of two vector is 0, if the dot product of two vector is 0, then those vectors are perpendicular to each other. So if this is normal to the surface, then this will lie in the tangent plane of the solution surface, the tangent plane of the solution surface. So if we draw any tangent to this solution surface, the direction of that tangent, if we draw any tangent to this solution surface, then the direction of that tangent plane will coincide with the instantaneous direction of this vector field, will coincide with the instantaneous direction of this vector field. Next, what we did, so since we are in 3D plane, suppose this is your x-axis, this is x-axis, this is your y-axis, and this is your z-axis. So solution surface will be like this. Now, if we take any point on this solution surface, say x, y, z, say this point vector is denoted by r. This point vector is denoted by r. Now, what I did, I parameterize. I say that x depends on a parameter s, y depend on a parameter s, and z depend on a parameter s. Now, let me ask you a question, very basic question. This is t, this is x, and don't go over 3D plane, just talk about two dimension, and please respond me. So when we define dx, the rate of change of x with respect to t, so how it is written x t plus h minus x of t upon h, limit h tends to 0. So this is the derivative. This is the derivative of any function f x that is varying with t. So how, suppose this is your curve, and this is your curve, and this is x, and this x of t, and this is x t of h, and then we connect this chord, and as soon as this chord become tangent to this chord become tangent to this, what is that? That is derivative. It means if x is depending on the parameter t, so the derivative of this x with respect to the parameter is nothing but tangent to that chord, tangent to that curve. So if r vector that is depending on a parameter s, so what will be dr over ds? Is not it will be tangent in x direction for the first component, for the second component tangent in the y direction, and for the third component tangent in the z direction. Now can you relate the how I was saying tangent, because a lot of you were confused. So this theory is coming like this is very basic bachelor's theory. That's why I was not going in the detail. So this is the theory. How I told you that if r is any position vector, if r is any position vector that is depending on a parameter s, so the component of this will also be differentiated. How we will differentiate the position vector? Like this. So if r is a position vector, then the derivative of this position vector with the variable, with the parameter s, is going to be tangent in each direction. The first component is denoting the tangent in x direction, the second is denoting the first is x, the second is y, and third is z. So this is going to be a tangent. This is going to be a tangent. Now, as I said, that if you take any point on the surface, then the tangent at that point is going to coincide with the instantaneous direction of this vector field. So because of that, we could write dx over ds is A, and dy over ds is B, and dz over ds is C. Now we have reduced our partial differential equation, we have reduced our Cauchy-Linear partial differential equation to a system of ordinary differential equation, Now as soon as this vector field A, B, C, that is depending on x, y, z, will be continuous and ellipsis function, then we are going to get a unique solution under some initial condition. And what will be the initial condition? So to solve any PDE, we also need an initial condition. So I get the initial condition z x comma y is 0 is nothing but z naught x. So this is the initial condition. Now if I parameterize this initial curve, x equals to xi, y equals to 0, then what will be z? Z will be function of z naught xi. So we can solve this partial differential equation under this initial condition. Now when you will be solving this system of ODE under the condition that A, B, C are ellipsis function, then using the existence and uniqueness theorem, we can say that we will be getting the unique solution of this system of ordinary differential equation. So x will be function of xi comma s, because xi is an initial condition. Y will be function of xi comma s, and z will be function of xi comma s. So this is the solution. Now you can see that this is the solution of a PD, but this is a parameterized solution. Our aim is to find out the solution such that it depends on x comma y. Now to express this form, we need to express xi comma s as a function of x comma y. Xi comma s as a function of x comma y. And in what case it is possible? If the transformation from xy plane to xi comma s plane, then xi comma x can be expressed as a function of x comma y when the Jacobian of that transformation, using the inverse function theorem, the Jacobian of that transformation is non-zero. So we calculated the Jacobian of this transformation, that is x xi.
I just wanted to ask which of the various inverse function theorems you are referring to.
Sorry?
Like, if I just wanted to know, like, the inverse function theorem, like, assures you that if you have like a non-zero value of a function, then it's like invertible in some boundary in which you have defined that function.
Yeah, and we don't talk about the boundary. We always talk about the domain. Have you seen that when we take any domain, then we say that it is an open set?
Yes.
Why we say that? So there is a reason why we every time when we talk about the domain, then we say that it is an open set. Just try to understand.
Because you needed to define like continuous functions.
Differentiable function. So the
Yeah.
differentiability is not defined at the corner. So that's why we take open set, so that we can, because at the corner you can draw more than one tangent. So you can get more than one differentiable. That's why it is not defined on the boundary. We are taking only the domain. That is the reason, excluding its boundary. For the boundary, we need to follow something else. So this we only talk in some domain omega. Yeah, so inverse function theorem, this is a very nice function, very nice theorem, and I think you might be aware because you took the course of real analysis in the last semester. So after the Rolle's theorem and Lagrange's mean value theorem, we also study the inverse function theorem when we take the function of two variable and transformation from one plane to another plane. So this is the topic of real analysis, and you might be, and this is a very important theorem. And I would like to ask, even I would suggest to all of you, please keep reading the basics of your mathematics, because in the last semester we talked about the uniqueness of this solution. Now Camilo and Yvonne were present in the class, so I expect a lot that you guys know how I proved the uniqueness of this system of ordinary differential equation, basically using Picard-Lindelof theorem, or we simply call it existence and uniqueness theorem. But the inverse function theorem, because we are studying a higher order PD, not a basic PDE. This course is basically aims to a master and PhD student, because I am teaching very basic, because this is basic, your basics would be strong. So please.
The inverse function theorem states that if the Jacobian is invertible at zero, then it exists a neighborhood that contains zero.
No, Jacobian should be non-zero even in the small neighborhood. That's why you are saying that Jacobian is non-zero even at zero.
Yeah, that's why it's invertible at zero, right?
Yeah, because the solution is continuous. So using the property of the continuity, we say that the Jacobian is going to be non-zero even at zero.
Yeah. So yes.
So if we understand these things with the help of geometry, then this curve gamma was our initial curve, and the characteristic was going along this. So S was varying along this, and this gamma is where xi is varying. So if this key is a point xi comma 0, so the solution should be unique even in the small neighborhood. So because of the continuity of the solution, the Jacobian should be non-zero even at s equals to 0. Even at s equals to 0. Now here you can say that characteristic is going along this. Now if two characteristics will intersect, suppose this is a characteristic and this is a characteristic, they intersect. So along this solution u is constant and it is something. Along this the solution u is constant and this is something. So these two solutions are different, but they are intersecting. It means you are saying that at one point you are getting two solutions. So in that case, you will have either multi-valued solution or it is not defined, so no solution. That is the case of shock wave and rare factor wave, which we are going to study in a very broad way. So that's why I did not explain, because there is a geometry and we are going to understand the geometry of that thing, how the solution of this differential equation is not well defined in the whole domain. It breaks down after a finite length of time. So we are going to study that in detail. But here we could see that we saw an example where we don't have the facility of solution. We have no solution for that, if you remember an example. So what happens, this is the initial curve gamma and a characteristic emanates from here, a characteristic emanates from here, and what happens is it goes and cut this curve gamma at some point. It characteristics is a straight line or it can be, so it cut the initial curve. So this gives us whether we are going to have multiple solution of those. However, we could see an example where we have no solution. So we have seen these things. Now, if you guys are confused at any single point, then please ask me, because we are going to proceed towards the characteristic methods for fully non-linear equation. That is going to be little bit difficult. But if you understand these things, then you are going to understand those things very easily. I already have uploaded the notes, so you don't need to write anything. You can go to the classroom, and today lecture is, I think, lecture number 6. So you can have a look at that. You don't need to write anything. Yeah, so it is uploaded with the lecture 6, so you can have a look. And before proceeding to the theory, I would like to discuss one thing. So in the Cauchy linear partial differential equation, where I give the notation this equals to p, this can be z or this can be u. It is up to you. If u is dependent variable, then u will be known of that, and if z is in the dependent variable, then it will be defined, so don't worry about that. If I am giving this notation, then the Cauchy linear partial differential equation is like a p plus b q is equals to c. This was the Cauchy linear partial differential equation. Now, according to our discussion, we get to know that this is the integral surface or solution surface, and the normal to this solution surface is PQ minus 1. The normal to the solution surface is PQ minus 1. Since it was linear in P and Q, it was linear in P and Q. So the rest is going to be free from the derivative of the unknown variable. This is going to be some known function, and it is going to be some trivial function, like you will already be aware of that because it is free from the derivative. So in that case, if this is normal, then this is going to lie in the tangent plane, and since it is not depending on PQ minus 1, it means this is a Cauchy linear partial differential equation that is linear in P and Q. Because of that, this will represent a plane, either an axis or plane. However, if this is your first order PDE, and it is non-linear, say it is like P square plus Q square plus PQ equals to Z. Again, the solution will be of this form, is not it? And what will be the normal to that solution? This. The normal to that solution will be this. However, if we are going to express in this form, then this function will be depending on P and Q, because this is not linear in P and Q. Since this is a normal, so in somehow you are able to express this form like some A, B, C, say capital A, capital B, capital C, and dot product with P, Q minus 1 equals to 0. Then this function A, B, C, it will be independent of P and Q. Is it independent of P and Q? Can you analyze with this?
No, must be
No. Exactly, no. We don't know what is the form of that, but it is for sure not independent of this P and Q. So because of that tangent field, that's the tangent field whose direction coincide with the direction of this vector field, is not going to be independent of the derivative of z. It means this is a non-linear problem, and because of that, the tangent plane will not be a plane. However, it will generate a surface, because every step you are going to solve the problem, it will generate a surface. So we are going to see that. It was just a basic idea how I am saying that. So this will coincide, this will lie in the direction, in the tangent field of the solution surface. So how it will generate a cone, a cone, and that the generator of that cone, like suppose this is the cone, so the generator of that cone, suppose this is the generator or this is, it is going to touch your tangent plane of this integral surface, and this comes from the theory of the differential geometry, and let me state the theorem. So the Monge cone is a proper cone because a non-trivial, this is a non-trivial function, it is a non-trivial function, and also depending on the derivative, non-coaxial one parameter family of plane through a fixed points envelops a cone. So it is going to envelop a cone because of that property. Now what happens? Let's see. See, in the first way, when we are studying any topic, it is going to be a little bit complicated. But when because here we are not studying only partial differential equation, we are also seeing the geometry of that. So in the first way it is going to seems little bit difficult, but as soon as you will understand the geometry in your mind, you will try to visualize those things. It is going to be like as you said that the last day you studied the subject and you could understand. So I understand that once I am explaining, just ask your trivial doubts and then study at your home. And if you are not getting the thing, then again ask me. I am here to explain again and again. And I'm damn sure if you are going to study with your own self, then for sure it is going to be very easier. That is my understanding for all of you. So the method of characteristic for the fully nonlinear equation, for the fully nonlinear but first order. So rather than writing here, I just wanted to open my notes because there are something that I have written and I just wanted to explain. But before that, let's have a look. For the fully nonlinear, first order nonlinear equation. So this is the third topic of your chapter first. Third topic, yeah. So here we will discuss the problem of finding the solution of a first order nonlinear partial differential equation in three variables, where one is unknown variable, that is your z, and two are your known variable x and y. So this is your first order nonlinear equation in three variable x, y and z. So z is your dependent or unknown variable. This is your unknown variable that is varying with x and y, and x and y are your known variable. For here you already know that this p is nothing. I just I'm just doing this thing simple so that it will be easy for us to calculate, because every time writing del z over del x is little bit complicated. So that's why you can also adopt the same notation even for your exam, because I understand what is this. So the p, derivative of the dependent variable with respect to x, and q, the derivative of the dependent variable with respect to y. We also assume that the function possesses continuous second order derivatives with respect to its argument over a domain. We also assume the same thing in the previous problem. In the domain omega, so omega is some domain, and since when we were taking time and x variable, then omega was contained in closed interval 0, infinity, r cube, if we were in R3. So this one, but here this is x and this is y, so only two dimensions, so it is going to, omega is going to contain in r square. Okay, so in the domain omega, and this domain omega is defined in such a way that x, y and z belongs to, and also its first order partial derivative belongs to the omega. It means we are assuming that the solution is continuous. The next thing, we are assuming that fp or fq is not 0 simultaneously. So can you guys tell me what is the meaning of fq and fq is not 0 simultaneously? Anyone? Fp, that is the derivative of this function with respect to p, and the derivative of this function with respect to q does not vary simultaneously. It means x square plus x square is not going to be 0. Anyone explain? This is very simple.
The only thing I can think of is like maybe what like transforming that into a like determinant of a Jacobian.
No.
Maybe.
No, this is very simple thing. Don't go in that much complicated. You are thinking a very forward thing that is very complicated. Very simple. Anyone else? Why I am saying that fp and fq is not 0 simultaneously? This is very simple, very simple logic.
Yeah, that if one is 0, then the other one cannot be 0.
Why? What is the criteria behind this? If I am writing a line, so I'm not just stating a vague statement. If behind every line there is something which is related to the definition of your partial differential equation. So just think for a minute. If you're not getting, then tell me. Everyone, like Camilo, Rebecca, anyone. If it is silly, then still you can say me. It might be possible because this is a very silly reason, but still I am asking. Okay.
Well, we know that P means
This
in a like in the canonical form of a partial differential equation that has just like two derivatives with two different derivatives with respect to independent variables P and Q. If one is 0, then the function do not changes in one direction,
no,
but the
it's very
but
complicated. That's what. Suppose this is F, and I'm taking
sorry.
F P plus Q minus 1 equals to 0. So del F over del P, that is 1, and del F over del Q, that is 1. So here it is not 0, that's why it is partial differential equation. Suppose del F over del P is 0, it means this is independent of P. So this is cancelled out. Del F over del Q is 0, so it will be independent of Q. It means there will be no derivative of the dependent variable. It will be an algebraic equation. Suppose you are considering a function that is independent of P and Q. So it will not contain these two variables. It will not contain these two variables. So what does that means? That this function f is independent of the derivative of the unknown variable. And if it is independent of the derivative of the unknown variable, then it is an algebraic equation. It is no more a partial differential equation. The logic was so simple. That's why I was asking. I told you that this should not be 0 simultaneously. Simultaneously means at the same point this should not be 0, because at the same point it is 0. So at the same point this function will reduce to this function. And what is this? It is an algebraic equation. It is not a partial differential equation. Did you get that point?
Yeah. Clear.
So every time when we write something, there is a reason behind that. So FP or FQ, either FP is 0 or FQ, both cannot be 0 at the same point, because if both are simultaneously 0 at the same point, so because of the continuity of the equation, they are going to sign 0 at all the other points, and in that case we are going to get an algebraic equation, and we will not have any partial differential equation. But we are discussing the characteristic method for a partial differential equation, for a first order partial differential equation. So that's why at least one of them should be non-zero, at least one of them.
I'm a little bit confused with the what you just erased. The why we can write f equals to p plus q minus 1 equals to 0. Like that's a partial differential equation, right?
That's what I was saying, that if p was coming 1 there, that's what I was saying. If I am taking this partial differential equation,
Yes.
then if p was 1 and if q was 1, that was not equals to 0. So that's why it is a PD. If this is going to be 0, so there will be no p. And if this is equals to 0, then there will be no q. It means we have simple f equals to -1.
Equals to 0. Yeah. Okay.
Yeah, so that was the thing. If fp and fq is going to be 0, in that case, we will have an algebraic equation rather than a partial.
Yeah, if we eliminate both of the derivatives, yeah, we don't have any rate of change, and the idea of differential something just disappears. You just have a function.
That's what I was saying, that don't think so complicated. Some things are very easier when we study something. So that the PDE, this is your PDE first. So the PDE one establishes the fact that every point of the region there exists a relation between the numbers P and Q. Now we know that whether it is a Cauchy-linear or it is a non-linear partial differential equation, we will have the solution like this, and because of this solution P, Q and -1 is going to be normal to that integral surface, that solution surface. And if we write in this form some a comma b comma c dot this equals to 0, so we will have a function of the form phi p comma q equals to 0. This defines the direction of the normal. So this will be the direction cosine of the tangent, and this will define the direction of the normal. So we can express the given partial differential equation in this form. Can I open the notes and just can state those things, and then we will come back when we will have a derivative. So this was the lecture note of today. So the numbers P and Q such that phi P comma Q equals to 0, which defines the direction of the normal. So this is coming with the fact that phi P comma Q, that is basically vector A, vector B, vector C dot P comma Q comma -1, that is equals to 0. So this will also be depending on P and Q because this is a fully non-linear partial differential equation. This is a fully non-linear partial differential equation, but the solution is going to be in this form. This is your first order partial differential equation. So solution is going to be in this form because of this P that is del Z over del X, this Q that is del Z over del Y, and this -1 that is del Z over del Z will be defining, that is basically gradient of this Z. Say this is F equals to Z X comma Y minus Z. So the gradient of this F. So this is going to be the normal. And since if it will be the normal, so this will define a function which is connecting P and Q to the direction cosines of the tangent planes. So thus the direction of the normal to the desired integral surface at a certain point is not defined uniquely. Why I am saying that it is not defined uniquely? Because this is going to be some function P and Q, and we can change its criteria, like we can express it in different forms. So earlier, since these were constant for the Cauchy-linear, these were independent of P and these were independent of Q. So because of that, we have a unique way to express. But here we don't know what will be the form, so it is not defined uniquely. However, a certain cone of admissible directions of the normal exists satisfying the relation this. Therefore, the problem of finding the solution of equations first reduced to finding an integral surface, the normals at every point of which are directed along one of the permissible direction of the cone of the normal at that point. And let me explain you in more detail. So what happened? See, we were saying that suppose this is your integral surface or solution surface. This is your integral surface, and this is some point, say x0, y0, z0. Now the normal PQ -1 will be normal to this surface. So direction of this normal is nothing but PQ -1 because of this. Now since this function is not a linear function, this is not a function independent of P and Q, it is also including the derivative of the unknown variable. Because of that, this will not be a plane, this will not be an axis like thing. So what will happen? This is your tangent plane. So the tangent plane which pass through, it will envelop a cone. It will envelop a cone, and this cone.
Sorry, but if you can restrict some things about A, B, and C, because we are studying quasi-linear partial differential equations. So you know that I don't know, A cannot have the derivative.
Yeah,
Like,
it's linear. Yeah, so that's why we have known function, we have known direction field, but here we don't have a known direction field. That is also varying with the derivative. So it is a function of del z over del x and del z over del y. So the tangent will not be a simple tangent in the surface. However, it will envelop a cone, and one of the generator of the cone is going to touch the surface of that. It is going to touch touch the integral surface like the tangent. So this will envelop a cone, and suppose the below of this cone is going to touch your integral surface, so it will envelop a cone. Every tangent field will envelop a cone here. However, when this A, B and C are independent of P and Q, so this will be nothing but a axis of that cone only. That will be a simple plane. Because of the linearity of this function, it is not depending on P and Q. And if it is
but the where the cone and the integral surface intersect, that's just a single point, or it's like
a line, it is like a line. It will be like the one of the generator of, you know that the cone is generated by a line, an axis. So it will be one of the generator of the cone. You can pick any side.
I don't know how to see like an intersection of a cone with a integral surface.
Okay.
Like,
so
and like to imagine that that's just like a line. I don't know how to.
just let me explain you.
Even just thinking about like a surface and a cone, I don't know even how to like put the cone in the surface and make a line. It should be, yeah, if you put a cone like just barely touching the surface,
Let me try.
you can get like a line.
Let me explain. So can you see that this is some kind of surface in 3D?
Yes.
So this is z-axis, this is y, this is x. So g-axis is like this. So because of that, we are finding out y, and the x-axis is going below. So because of that, now what I am saying that the direction of the normal, like will be touching the tangent plane at some point x naught, y naught,
Yes,
z naught.
it's a vector.
Yeah. So this point will lie in the tangent plane. However, since it is it will be the intersection of different kind of tangent plane, and whose normal is nothing but p, q and -1. So what I am saying that this is a point in the integral surface, so it will be like a cone. And
Oh yes.
the axis of that cone is going to be the normal, and if the axis of that cone is going to be normal, so it is generated, at least one of its generator is going to touch your tangent plane. At least
Yeah,
one of the generator is going to touch your tangent plane, because of the dependency of this function on P and Q, we are not going to get a plane. In other, it was just an axis. Now it is depending on P and Q. So because of that, it is going to envelop a surface, and that envelope will be a cone, and that is known as Monge cone.
So the vortex where all of those those are solutions, right?
Exactly. So
those all of that envelope and
surface.
yeah, those all the vectors that are inside that cone are solutions. Not all of the, no, yeah.
which will touch your integral surface, which will touch your integral surface. So that's what we are saying. All are not going to touch the integral surface. Only one generator will touch the integral surface, and then it will start to generate.
Yeah, but those where it touches, all of the other vectors that are solutions that generate that cone will come up from that point, right? All
Yeah,
of
so
the others.
that is the generator. That's why when every time when we talk, it is a direction cosine. It is not the tangent. The tangent and the integral surface will coincide with the direction cosine of this. That's why we say that. We don't say that it is a tangent. It will be parallel to the plane. It will be even parallel to the tangent plane. But it is not, it might be tangent exactly or might, but it is a direction cosine. So its direction and the direction of the tangent to the integral surface are going to be same.
Okay.
And we know that if we have this first order partial derivative, whether linear or non-linear, so the solution is going to contain two constants A and B, which is called a complete integral. We have already studied this complete integral. Next again, we are coming to the Cauchy method of characteristic. Again, we are going to use the previous theory. So what we know that the integral surface, again I am writing this equation, f x y z t comma q equals to 0, g equals to z x comma y is an integral surface of equation number first that passes through a given curve, x equals to x naught s, y naught is equals to y naught s, and z naught equals to g naught x, may be visualized as consisting of a point lying on a certain one parameter family of curves. So if you remember, when I parameterized any point on the surface, I am using the initial condition g of x, y of x equals to z naught of x, using this initial condition, and with this parameterized we got the solution depending in two variable. Basically I took xi, so here I am taking t. This is the theory which we already have studied. So that's why I revised those theory. So it will be depending on two variable t comma s, whereas is a parameter of the family called characteristic. So this gamma t is varying along this and s is varying along this. That is the characteristics. Whereas is again I am opening the notes. I have written everything very clearly there. So the integral surface z equals to z equals to z x y of equation first was your this equation x y z p comma q equals to 0. That passes through, this is passes you can correct it, through a given curve. This was the point, like if I took an integral surface, so here I took a point x, y and s, and this x, y, s was depending on a parameter s. So because of that, dr over ds was the tangent at that parametric curve. So I am denoting it x naught, y naught and g naught, specifying it. So maybe visualize as consisting of points lying on a certain one parameter family of curves. So when we solve this curve using the initial condition, we got a one parameter family of curve that is depending on a parameter s, and this s is nothing but characteristic. This is emanating a characteristic, and this t is nothing but the initial condition. So this was a gamma curve and this was the emanating. So s was varying along this and t was varying along this. Hence our aim is to discuss the Cauchy method. The method of characteristic for the fully non-linear differential equation is known as Cauchy method of characteristic. And
but just to confirm, the the solutions are lying on the integral surface. Yeah, we know that, like, without doing any calculations of any partial differential equation, we know that the solutions lie on a integral surface. But this solutions are like are yeah, functions in functions that take two parameters and associates those two parameters to a number in the real line. So you have, yeah, a curve that it's living on the integral surface, but those curves are special because like all of the integral surface is a solution, but why do we just select like uh like a string of that integral surface? That's why I'm what I am understanding about the solutions. Like the solutions are like strings in that integral surface.
Yeah, you can say that is a string, but let me clarify one more thing. It will there will be non-linear interaction between each string. If you are talking about one string, suppose x naught, y naught, and s naught, z naught is a point on one string, then it might be possible that the second string is also crossing through this string. In the linear case, the string was going to be like this, simple. But because of the non-linearity of P and Q, even for the Cauchy-linear, so that's give you the multi-valued solution, because when both the two string will coincide, because these are characteristics, so solution is constant along this characteristic and solution is constant along this characteristic. But the characteristics are going to change, like the relation between x and t are going to change. So you are saying that when two characteristics are coinciding, so you are finding a multi-valued solution here. Multi-valued or no solution, because
Yes.
at one point you are getting two solutions. So that is violating the theory of differential equations. So that comes in the category of the shock wave or discontinuous solution.
Okay.
Yeah, so in the linear case, these characteristics were not going to coincide, but in the non-linear case, who knows? We can already see that in the one.
Yeah, maybe we cannot say that they are unique solutions.
Exactly, they are not unique solution unless until this t comma s again can be expressed as the function of x comma y. So that's why I am not going back. I am just saying that x, here we are getting the parameterized solution. But with this parameterized solution, we can talk about the unique solution only when this parameterization has a non-zero Jacobian.
Oh, okay.
Like everything is interconnected, but you just need to pay little bit attention if you know those things. So that's I wrote the solution as a parametric solution. Here our aim is to discuss the Cauchy method for solving non-linear first order equation. Non-linear first order equation, which is based on the geometrical consideration, because here we are discussing the geometry. We are saying the characteristics are either going to intersect or going to separate it, representing a unique solution or a multi-valued solution or no solution. S of equation first in xyz space. So this is an integral surface, and depending on this integral surface, p, q and minus 1 are going to be the normal to the direction ratios of the normal to that integral surface. Now the PD1 states that at a given point, if you choose any point, if we choose any point on this x naught, y naught, suppose this is the point x naught, y naught, z naught, and you take the differential equation, you take the partial differential equation at this point and you express this. Now, since This is a non-linear partial differential equation, that is non-linear in P and Q. So even at a single point, it is need not be necessarily linear. It might be non-linear or non-linear. Suppose if Q naught vanishes, and P naught is only function, so it might be expressed as a linear, but it might be possible that it is not a linear. Hence, all the tangent planes to the possible integral surface through P form a family of planes enveloping a conical surface called Monge cone with P as its vertex. In other words, the problem of solving the PD first is to find the surface which touches the Monge cone at each point along a generator. So this is our aim, to find the thing. Now we are going to see an example for what I am saying. So this is a non-linear partial differential equation. You can see. Now at every point of the xyz space, the relation of 2 can be expressed parametrically. So here we know that how this can be if we choose this parametric form cos hyperbolic mu and q equals to sine hyperbolic mu, then P and Q, so P square minus Q square will be 1 because cos hyperbolic square minus sine hyperbolic square is 1. So this is the parametric representation. Actually, every time you won't be able to find this parameterization, that's why I am giving you a simple example just to visualize the things, what is happening. Then the equation of tangent plane, okay, let's come to the point. Suppose this is x naught, y naught, z naught is the point from where the normal is emanated. This is the direction of the normal, and this is x, y, z, some point in the surface. Then we know the normal and we know the from where the normal is written. So the equation of the tangent plane in the variable x, y, z can be written as x minus x. Now this is the simple differential. This is simple geometry. The direction of the normal, like in x direction, so x in x direction, the normal is p plus y minus y naught. The direction of the normal in y direction, so that is q, and plus z minus z naught, the direction of the normal in z direction, so that is minus. So the equation of tangent planes at x naught, y naught, z naught can be written as this. Now we know that this parameterization P and Q say this was your equation number first. This
why do we write x minus x0 p plus y minus y0 q equals to c minus c0?
Using theory of geometry, we know that if there is a normal in a surface, there is a normal at a surface, and the normal is defined at a point x naught, y naught, z naught as a fixed point, then the equation of the tangent plane can be written as x minus x naught into.
Oh yes, it's just like the dot product.
Exactly.
No, it's not the dot product because yeah, you construct the first the vector from x to the x0.
X minus x naught, and then the normal.
The dot product.
Yeah. So that is the theory, like that is the basic geometry. I think I am using a lot of geometry, but don't worry about that. This is a very simple geometry because this is going to be easier for all of you. So let P be the vertex and Q be any point on the generator. Since here this is a non-linear partial differential equation, now P is a vertex and Q be any point on the generator of the cone, then the direction ratios of the generators are this, because here we could see that the direction ratios of the generators were this vector field. So the direction ratio of the generator is x minus x naught, y minus y naught, and z minus z naught. Now the direction ratio of the axis of the cone, which is parallel to x-axis. So let me plot this thing firstly. So this is z, this is y, this is x, and this is o. So you can see that this is z direction. This is going to be coincide with the direction of x, and this is going to be y direction. So this generator, I am saying that the direction of the generator is the x-axis. So this is going to be the direction of the x-axis basically. So what is the direction cosine of the x-axis? What will be the direction cosine of the x-axis? On the x-axis, y is 0 and z is 0. So the direction cosine is 1, 0, 0. So, are you understanding what I am saying?
The direction cosines are just like the projection of.
Direction ratios, you can say that.
Huh?
Direction ratio or direction cosine. So for the x-axis, y and z are 0 at x-axis. So direction ratio is 1, 0, 0. Like basically how you write basis of a vector. Like you write the basis on x-axis it is 1, 0, 0. On y-axis it is 0, 1, 0. On z-axis it is 0, 0, 1.
Mm-hmm.
So it is like that. So now the direction ratios of the axis of the cone, which is parallel to x-axis, are 1, 0, 0. Let the semi-vertical angle of the cone be pi by 4. Then cos of pi by 4 will be the. Now you can see that x minus x naught, y minus y naught, and z minus z naught are direction ratios of the generator, and we are taking this as generator, and with the generator the x-axis is making an angle pi by 4. So because of that, cos pi by 4 is x minus x naught into 1 plus y minus y naught into 0 plus z minus z naught into 0 upon under root x minus x naught square plus y minus y naught square plus z minus z naught square. So when you will solve this, you will get because cos pi by 4 is 1 upon square root 2. So just take square of both sides and solve this. So you will be getting this. Now you can see that this is a right circular cone with semi-vertical angle pi by 4. This is a right circular cone with a semi-vertical angle pi by 4 whose axis is the straight line passing through x naught, y naught, z naught. This was the point P, x naught, y naught, z naught, and this was Q, x, y, z passing through x naught and parallel to, because we know that this P is parallel to z-axis. This p is parallel to g-axis and this was parallel to x-axis. And this is our Monge cone, which is a right circular cone with semi vertical angle pi by 4. Don't write anything, everything is written in your notes. Now, with this description, we got to know that since an integral surface is touched by a Monge cone along its generator, so we must have a method to determine the generator of the Monge cone. Once we will be able to determine the generator of the Monge cone, then we will be able to write the parametric solution of the given nonlinear partial differential equation. Now, how we will do that? It may be noted that the equation of the tangent plane to the integral surface z equals to z x comma y at the point x naught, y naught, z naught is what is the equation of the tangent plane at the point x naught, y naught, z naught? What is the tangent plane to this integral surface which pass through the point x naught, y naught, z naught?
It's the partial with respect to the partial c with respect to x, the partial of comma.
That is normal. You are saying normal.
Yeah, we need to construct the gradient of the function.
So I'm not talking about the normal. I am talking about the equation of the tangent plane passing through the point x naught.
You have to put the coefficients and then the partials.
So what is? I am giving you the point x naught, y naught, z naught. I am giving you the integrals.
X0, Y0. Dot product, that vector dot product with p, p, q, and minus 1 equals to 0.
Is it, Camilo?
Yes.
Yeah, I think so.
Sorry?
Yeah, I think so.
No. I just in the previous I said that if this is the point that is x naught, y naught, j naught, g naught, and it is lying in the surface. So if we take any general point x, y, and z. And
oh yes, we need to put x minus. Yeah.
Another is x naught, y naught, z naught. So it will not be representing tangent.
Yeah, it would be like a constant vector.
Because you are giving a point.
Yes.
This is the equation of tangent plane. Equation of tangent plane to the integral surface z equals to zx comma y at the point x naught, y naught, z naught. So this is the equation of the tangent plane. Now the given nonlinear PD can also be written as the given non-linear PD can be rewritten as passing through the point x naught, y naught, j naught. If we say that this is the nonlinear PD passing through the point x naught, y naught, j naught, g naught, p comma q, then we can express as q as a function of x naught, y naught, j naught, p, or p as a function of x naught, y naught, z naught, q. So this is the way you can express, indicating that P and Q are not independent. Unfortunately, they are not independent because they are non-linear function here. At each point of the integral surface S, there exists a Monge cone which touches the surface along the generator of the cone. We already have discussed at each point of the surface S, there exists a Monge cone which touches the surface along the generator of the cone. The lines of contact between the tangent plane of the integral surface and the corresponding cones, that is the generator along which the surface is touched, define a direction field on the surface. So just try to understand. I am saying that the generator of this cone touch the tangent plane of the integral surface. So there will be a line because a cone is touching a surface. So that will draw a line. So the line of contact between the tangent plane of the integral surface and the corresponding cones, that is basically the generator of the cone along which the surface is touched, define a direction field on the surface. That will define a direction field. And these directions are called the characteristic direction. That is the generators along which the surface is touched, define a direction field on the surface S, and that direction field is the direction of the characteristics. So these, basically our aim was to identify the characteristic direction of the non-linear partial differential equation. So these directions are called the characteristic directions, also called Monge directions on the integral surface S. Basically, I am representing this S as integral surface or solution surface, whatever you. And lie along the generators of the Monge cone, because we know that the line of contact of the integral surface is going to coincide with the one of the generator of the Monge cone. So, and lie along the generators of the Monge cone. The integral curves of this field of direction on the integral surface define a family of curves called characteristic curves. The integral curves of this field of directions
I must catch
on
up.
the
Is very clear that.
Integral
You explain.
surface
I must catch up.
S define a family of curves called characteristic curves. So just try to understand, this is your integral surface or solution surface. Now, as I told you, the tangent at the integral surface is going to coincide with the one of the generator of the Monge cone. So just try to understand, this is a cone, so it will be like enveloping a surface. So if it is enveloping like this, so at least one line is going to lie in this tangent plane of the integral surface. Can you?
Oh, so the cones are not like vertical cones, like
No, that's what I was representing.
yeah, the cone is like embedded.
Yeah, so
Well,
this was
like
z-axis. That's why this was z-axis and it was lying here. It was vertical, but it was z-axis.
it's like if a cone, this is like the integral surface. The cone is like making like
So it is
I don't know.
involved that surface. Yeah.
Yes.
And one of the generator is going to lie in the tangent field of the integral surface. So you can see here I am drawing it vertically, but it was g-axis. So because of that, at least when it is enveloping the integral surface, one generator which is generating the Monge cone is going to intersect with the tangent plane of the integral surface.
And what about the 2 points where the cone touches the integral surface? Well,
that is unknown to us. That we are going to derive. What will be that characteristic where the tangent at the integral surface will interact with the generator of the integral cone. That will form a direction field, and that will be the direction of the characteristics. So we are going to determine what will be the characteristics of the nonlinear using this Monge cone method. That is our aim. Still, till that time, I am not doing any kind of derivation. I am just giving the explanation. I am just trying to make you understand how this thing can be visualized. The derivation I will start, but I think it will go tomorrow. I was trying to complete it by today, but it was really a very long topic. And
sorry if I make another question, like silly question, but I now I understand where is the axis of the cone, but the way you make a cone is like making if the cone has a circular base, it's easy to in each height like make a circle, and then the center of the circle is passing through the axis of the cone, and then you increase the radius, and then you are building like the cone. But right now the way that cone is going to be built, it's given by the partial differential equation, right?
Yeah.
That the equation tells you how to construct that cone.
Exactly. And if you will remember, so at this point, one normal will come. At this point, one normal will come. At this point, one normal will come. So at every point P, say x naught, y naught, z naught, where the normal P, comma q, comma minus 1 is defined.
Yeah, the normal is actually the axis of the cone.
Yeah, so this is the vertical. So when that A, B, and C were independent of P, Q minus 1, then it was not a cone, it was a simple axis. The axis that is known as Monge axis. But when this A, B, C depending on P and Q. In that case, this is not an axis. However, this is the envelope which encloses that integral surface, and one of the generator of this is an envelope. That envelope enveloping the integral surface and forms a cone, and one of the generator of the cone is coinciding with the tangent plane of the integral surface. However, when it was a Cauchy-Linear PDE, in that case, this was not a cone, this was a simple line. This was a simple line. That is known as our Monge axis in the case of Cauchy-Linear. Is it clear? Small 50%.
But right now we are studying quasi-linear differential equations, right? Partial differential equations.
We are studying the first order partial differential equation, and if you will take a quick look on your syllabus, then there is a topic. Just let me point out, because I need to cover all the topic. It might be syllabus, yeah. So when you will open the syllabus in the unit 2, the fourth 2.4 method of characteristic completely non-linear equations. Can you see that? So because of that, because this iconal equation is completely non-linear equation, so because of that we need to know this method of characteristic. Now we are going to find out the method of characteristic. Basically we are going to find out the Chapman equation, which solves a non-linear partial differential equation. So we are going to see the derivative, and I think it will take the whole Wednesday, and then on Thursday I will start the next topic. Riemann problem. I forgot to give you the definition of Cauchy problem. I will give. So this is the characteristic directions on an integral surface. The Monge cone can be obtained by eliminating P. Now I am going to go through the derivative, so I am just stopping here because the derivative is going to be long. So just read the geometry of this, and then we can derive the Chapman equation. Not basically Chapman equation, we can analyze the characteristic equation, and on the basis of the characteristic equation I am putting one portion in your assignment. You have to prove that, so tomorrow I will complete that. And if you guys have any doubts from the assignment, then you can ask tomorrow and try to submit it on time. After time you will be awarded only 80% of your marks, so just be consistent.
So the assignment, the first assignment has topics that we haven't covered?
No, I was talking about
okay.
assignment.
The second assignment has all of this
second assignment.
Chapman equation?
Chapman equation. So I will be giving that on Wednesday. I am going to share it tomorrow when I will be completing that topic.
Yeah, I thought first assignment has...
It is very easy. Like it will take only 30 minutes for all of you. Okay, so bye. See you tomorrow.
Thank you.
Yeah, bye.
Bye. Thank you.